Hello everyone. I would like to express about the extremely prescribed bridges, especially for design and long-term behavior. My name is Htoo, and my new student ID is 677006161. In this introduction, internally prescribed bridges are popular because they are durable, easy to inspect and repair, and cost-effective. With tendons placed outside the concrete, maintenance and replacement become much simpler. So extended tendons lose force over time from relaxation, temperature, creep, and traffic, which can lead to deflation and cracking. Traditional check makes these gradually change, so continuous non-disruptive monitoring is needed. This slide shows why existing monitoring methods are limited and how EM sensors solve the problem. Vibration and strain method need no loads and often give large error and real traffic. So how can solve this issue? The electromagnetic effects allow non-destructive force measurement, but traditional EM sensor had to be installed before tensioning. The semi-closed EM sensor fits this by allowing installing on in-service bridge. We tested it to rear bridge and confirmed reliable long-term performance. When it comes to objective of the study, our main goal is to develop and validate the long-term pressure monitoring method using semi-closed EM sensor, which can be installed after construction. We check the accuracy by comparing the sensor with the finite prediction from JGT 336 to 2018. We also observe how tandem folds change over a year under temperature and traffic effects. Finally, we assess whether semi-closed EM sensor can serve as a predicate alternative to traditional monitoring method. In this slide, the EM sensor detects these shapes using coil that measure changes in magnetic flux and convert them into a voltage signal. After calibration, this voltage stays as the actual tandem folds. So essentially, the EM sensor works as a non-contact transducer, allowing us to monitor tandem forces indirectly, accurately, and without interfering with the pressure. In this slide, external tenders are easy to input but sensitive to long-term effects, so monitoring is important. Figure 2 and 3 show two bridges where we install semi-closed EM sensor to track real tender forces. In this plan, we implement extended pressure monitoring using semi-closed EM sensor. This sensor can be installed after construction, making them suitable for in-service bridge. For custom plate 50-80 meter boxes cutter, we monitor tendons DW1 and DW3 at midspan because they are more sensitive to breakage changes and easy to access. For 40-meter bridge, each tendon has 25 strands, so we monitor three representative strands from W1 and W1 to capture tandem behavior. This semi-closed design is key. It allows installation around existing tandem and avoids the limitation of traditional closed sensor. This makes long-term tandem force monitoring practical and reliable in bridges. When it comes to finite element simulation of pre-stress loss, they carry out finite element simulation to predict pre-stress loss in both bridge. The purpose of the analysis is to create a theoretical reference so they could compare the expert tendon force with the actual force measured by EM sensors. They have as evaluate the accuracy and reliability of the monitoring system. And then we consider all major Prestressed loose mechanisms required by the GGT 332 2008 design specification. This includes friction loss along the tandem bed, anchoring slip, and elastic shortening of the concrete, and the long-term effect of the sterilization, as well as concrete creep and shrinkage. By including both instantaneous and time-dependent loss, the simulation provides a complete picture of how the tandem force should theoretically change over time. And then we developed a detailed finite element model of both bridge using meter saver. By using the meter saver, the custom plates and pre-stressed gather were models using pin element, and the external tender were defined according to their actual profile and anchor location. The model also includes the dead low, temperature variation, and light flow from highway traffic. Relaxing coefficient for the pre-stress we were applying to simulate long-term loss. The FE model produced two important values: the theoretical tendon forces after only instantaneous losses and the tendon force after long-term losses. These results serve as the benchmarks for the validation the EM sensor measurement and understanding the real pre-stress behavior in the field. Finally, we compare the every simulation result with the actual measurement from the semi-closed EM sensor. The every model provides two key reference values: the instantaneous tendon force right after stressing and the long-term tendon force after accounting for relaxing, creep shrinkage, and temperature effect. By plotting these against the measured data, we evaluate how closely the sensor captures real pre-stress behavior. This comparison have confirmed the accuracy of the semi-closed EM sensor and verify whether they can reliably reflect long-term tendon forces, radiation, and the real surface condition. When it comes to result analysis, we represent the monitoring results for the precast 40-meter box cutter. The purpose here is to understand how the extended tendon force behave under real surface conditions and how well the semi-closed EM sensor capture these variations. We focus on the short-term tendon forces behavior right after installation. The monitor strength showed that the EM sensor reading remains stable and consistent, confirming that the installation did not distribute the tendon and that the sensor can reliably track the initial pre-stress rate. We analyzed the daily and seasonal temperature effects. The results show a clear negative correlation between tendon force and temperature, meaning that the force decreases as temperature rises and increases when the temperature drops. This matches classical thermal pre-stress behavior and demonstrates the sensor sensitive to environmental changes. Finally, we examine the influence of live traffic loads. The research shows small but noticeable fluctuation in tendon force when heavy vehicle packs. These variations are within a few percent of the total force, which align with the expected behavior for Israeli tendon in 40-meter spans. Overall, the research showed that the EM sensor provides stable, accurate, and meaningful measurement for both environmental and traffic included tendon force changes. In this session, we evaluate the long-term behavior of external data based on 1 year of in-service monitoring. The semi-closed EM sensor continuously record tendon force together with temperature inside the box guide anywhere as to study tendon dependent effect under actual environmental conditions. The tendon force tend over times are shown in figure 11 and 12 for cuts in place and precast guide respectively. The results indicate that the tendon force replicate within about -3% to 5% of their initial measure value without any progressive downward trends. This behavior confirms that there was no abnormal stress loss or structural deterioration during the first year of service. In this session, the temperature has a strong negative effect on tendon forces as shown by correlation values of -0.77 and -0.59. Overall radiation stayed within ±5% with no signs of deterioration, confirming the EM sensor provides stable and reliable long-term monitoring. In this session, they analyze how the vehicular influence tendon forces. The figure 50 and 60 show the present trends cause small short-term fluctuation in tendon force profiles. The custom-based rate shows the slight force drop during heavy vehicle, even though the changes are very small within normal service limit. The precast rate exhibits smaller behavior with minor forces increase or decrease depending on the tendon's position. Overall, the vehicular index variation are limited compared to temperature effects, confirming the life load have only a modest influence on long-term tendon behavior. To conclude, this study showed that semi-closed electromagnetic sensors are practical and reliable tool for monitoring externally prescribed bridge in service. Because they can be installed after testing, they overcome the limitations of traditional sensors and allow continuous long-term monitoring. The results from both bridges indicate that tendon force remains stable over the first year with no signs of abnormal prescribed loss or deterioration. We also found that temperature is the main factor affecting tendon force, while trafficking load create only small short-term fluctuation. By comparing the external data with front element prediction, we confirm that the measurements are accurate and consistent. Overall, proposed method improves our ability to assess standard behavior and supports better maintenance and safety management for externally prescribed bridge. So thank you for your listening. I truly appreciate your attention. If you want something more energized and informative, I can tailor it.